Have you ever imagined a weapon so powerful it could wipe out the entire human race and give Earth a fresh start? We often think that supervillains who want to use such weapons exist only in Hollywood movies. But if such a person ever emerges, the weapon they need already exists. It is called the Doomsday Weapon, a device capable of triggering a mass extinction event, wiping out not just humans, but countless other species. This weapon belongs to a terrifying category known as weapons of mass destruction. The atom bomb, the one most people fear, is just one weapon on that list. But there are many others, each designed for a different kind of destruction. Some are built to kill people while leaving buildings untouched. Others are designed to spare both people and buildings, but wipe out all electronics. And some can even penetrate thick bunkers, leaving us with nowhere to hide. From chemical and biological agents to neutron bombs, cobalt bombs, hafnium bombs, the list is longer and darker than most people realize. In this video, we count down the 10 most terrifying weapons of mass destruction ever conceived. Number 4 is the dirtiest. Number 1 is the most powerful explosive device humans have ever imagined. Stay till the end, and you may find yourself wondering, how could humans do this to their own kind? Hi friends, welcome to a new video from Science Simplified for All. Conventional bombs like TNT and RDX cause damage through shock waves and fire. Even the biggest of them can only destroy a few hundred meters around them. But weapons of mass destruction are different. They are designed to affect thousands or even millions across vast regions. Some destroy instantly. Others leave deadly effects that last for years. This video ranks the 10 most dangerous weapons of mass destruction ever conceived. And just to be clear, everything mentioned here is based on open, publicly available information. No classified details are shared in this video. Among all weapons of mass destruction, chemical weapons have seen the most widespread use in history. And what makes them especially terrifying is not just how they kill, but how unpredictably and indiscriminately they spread. It was during World War I that chemical warfare made its devastating debut. Nations like Germany, France, Britain, Russia, Austria-Hungary, and Italy unleashed toxic gases such as chlorine, mustard gas, and phosgene on enemy soldiers. These chemicals caused severe choking, painful blisters, and internal lung damage, often leading to slow, agonizing deaths. But the danger did not end there. When the wind shifted, these same gases often drifted back towards civilians, or even the very soldiers who had released them. Though World War II saw limited use of chemical weapons on the front lines, their horrors were far from over. Nazi Germany used poison gas in concentration camps, exterminating millions. Imperial Japan also carried out chemical attacks on civilians in China. In the decades that followed World War II, the large-scale use of chemical weapons declined significantly. But isolated incidents continued to remind the world of their terrifying potential. During the Iran-Iraq War, Saddam Hussein used nerve agents like sarin and tabun, not just against enemy soldiers, but even on Kurdish civilians. These substances attacked the nervous system, shutting down vital functions within minutes. A single drop on the skin can be fatal. And more recently, during the Syrian civil war, the government was accused of using chemical weapons against its own population. Chemical weapons do not just kill, they terrorize. And that is why, even today, they remain one of the most feared and misused weapons of mass destruction in human history. Unlike conventional weapons, biological weapons use living organisms to unleash chaos. Bacteria, viruses, fungi, and even crop-destroying pests can be turned into tools of war. In some cases, it is not the organism itself, but the toxin it produces that becomes the killer. And once released, these agents can spread silently, multiplying, mutating, and striking without warning. Though the term biological weapon may sound modern, the idea of using disease as a weapon is centuries old. Historical records show that during the time of Genghis Khan, plague-infected corpses were hurled into enemy cities using massive catapults, triggering deadly outbreaks. And in the 18th century, British forces handed smallpox-contaminated blankets to Native Americans, hoping to break their resistance without firing a single shot. Fast forward to the 20th century. Japan is believed to have conducted horrifying biological warfare experiments in occupied parts of China during World War II. Using pathogens like plague, cholera, and anthrax, they caused the deaths of tens of thousands of civilians. No guns, no bombs, just disease, silently spreading through entire villages. During the Cold War, both the United States and the Soviet Union developed and stockpiled agents like smallpox, anthrax, and botulinum toxin. Though never used in battle, a few accidental lab leaks did occur, thankfully contained before disaster struck. But the close calls were enough to raise global alarms. Today, international treaties officially ban the use of biological weapons. But treaties are only as strong as those who follow them. With modern biotechnology, a small lab in the wrong hands is all it takes. Skilled scientists, willingly or unwillingly, could be forced to work for extremist groups. And in the age of global travel, a single carrier could trigger a global crisis. That is why biological weapons remain one of the most terrifying threats in the modern world. When people hear the term weapons of mass destruction, the first image that comes to mind is often the atom bomb, because it was the first weapon to show the world just how much devastation a single bomb could cause. This became terrifyingly clear when the United States dropped Little Boy over Hiroshima. Around 80,000 people died instantly, and a similar number were injured. Over the next 5 years, radiation fallout claimed another 80,000 lives. Buildings within 3 kilometers were either flattened or severely damaged. 3 days later, Fat Man was dropped on Nagasaki. Though technically more powerful, the surrounding terrain reduced the impact slightly. Still, these bombings showed the world that nuclear weapons were over 1,000 times more powerful than any conventional weapon used before. And to this day, those remain the only times nuclear bombs have ever been used in war. There are 2 types of nuclear reactions. The first is nuclear fission, where the nucleus of heavy atoms like uranium or plutonium is split apart to release energy. The second is nuclear fusion, where the nuclei of small atoms like hydrogen are fused together to release energy. Both release enormous energy, but through very different mechanisms. The bombs dropped on Hiroshima and Nagasaki were fission bombs. Each had an explosive yield of around 15 kilotons of TNT. However, there is a practical limit to the maximum power that fission bombs can deliver. This is because nuclear fission is a chain reaction. When one uranium nucleus undergoes fission, it not only releases energy, but also emits 2 or 3 neutrons. These neutrons then trigger fission in neighboring nuclei, and the reaction rapidly multiplies. Eventually, enough fission reactions occur simultaneously to produce an explosion. But here is the challenge. All of this must happen in just a few milliseconds, and during that time, the bomb must keep the uranium core tightly compressed. As soon as fission begins, the temperature and pressure inside the bomb begin to rise rapidly. If the uranium disperses too early due to this internal pressure, the chain reaction will stop prematurely. In the Hiroshima bomb, although it contained 64 kilograms of uranium, only about 1 kilogram actually underwent fission. The rest was blown apart by the explosion before the reaction could spread further. In other words, more than 98% of the uranium used in the bomb went to waste. Modern technologies have been able to slightly reduce this inefficiency, but even today, this wastage remains a serious drawback in fission-based nuclear bombs. This is why fission bombs, what we commonly call atom bombs, have a limit in their explosive potential. At most, they can produce yields up to around 500 kilotons of TNT. And that brings us to the next type of nuclear weapon, the one that changed everything. A hydrogen bomb is a nuclear weapon powered by nuclear fusion. Although it is called a hydrogen bomb, it actually uses the isotopes of hydrogen, deuterium and tritium. These fuse together to form helium, releasing an enormous amount of energy. This is the same process that powers the sun. Fusion requires extremely high pressure and temperature. But once these conditions are met, the process happens almost instantly. Unlike the chain reaction in fission, fusion is not gradual. A large portion of the fuel reacts at once, with minimal wastage. Fusion bombs also have no critical mass limit, which means more fuel can be packed safely into a single bomb. This gives them excellent scalability. And for every kilogram of fuel used, fusion releases far more energy than fission. More energy, less material, maximum devastation. All of these factors combined make hydrogen bombs vastly more powerful than atom bombs. So how do we create the extreme pressure and temperature needed for fusion, nearly 100 million degrees Celsius? There is only one practical method: using an atom bomb as a trigger. A hydrogen bomb begins with the detonation of a fission-based atom bomb. Before that reaction escalates into a full explosion, its intense heat is directed toward the fusion fuel using a special configuration. This rapidly raises the temperature and initiates fusion. That is why they are also called thermonuclear bombs. It is a bomb within a bomb. Due to this configuration, all hydrogen bombs have at least two stages. The first is a fission explosion that acts as the trigger but is still powerful on its own. The second is the fusion stage, where hydrogen isotopes react and produce the major share of the explosive energy. The total energy released is the sum of both stages. This two-stage design gives hydrogen bombs their immense power. While fission bombs top out at around 500 kilotons, hydrogen bombs can exceed 5 megatons. That is 10 times the explosive power, achieved through a different kind of reaction. There is another variant of the hydrogen bomb known as the clean H bomb. A major drawback of atom bombs is radioactive fallout. The fission byproducts are highly radioactive, and along with the unused fuel, they are vaporized by the explosion and spread through the atmosphere. These particles settle over wide areas, causing long-term contamination that can even reach neighboring countries. This fallout is the main reason for global opposition to atomic weapons. This is where the concept of the clean H bomb becomes relevant. Since fusion reactions produce very little radioactive waste, a bomb that relies mostly on fusion can significantly reduce fallout. Of course, a small amount of fission is still needed to trigger the fusion. In a clean H bomb, the fission stage is kept minimal, just enough to initiate the reaction, while most of the explosive power comes from fusion. This reduces radioactive contamination without sacrificing destructive power, making such bombs more diplomatically acceptable. However, building them is not easy. It remains unclear how many countries have successfully developed clean H bombs. Most nations prioritize maximum yield using full-capacity fission and fusion stages. Still, it is important to understand the fact that a cleaner, less contaminating hydrogen bomb is also possible. Most nuclear powers aim to keep their weapons compact while maximizing explosive yield, often without much concern for radioactive fallout. This is where the concept of the three-stage nuclear bomb comes in. So far, we have discussed hydrogen bombs where a fission explosion triggers a fusion reaction. But there is an advanced category known as fission-triggered, fusion-boosted, fission bombs, some of the most powerful ever built. The first two stages work as before. A fission trigger ignites a fusion reaction. During this fusion stage, a massive number of high-energy neutrons are produced. In standard hydrogen bombs, these neutrons go unused. But in three-stage bombs, they are key to activating a third stage. Surrounding the fusion fuel is a uranium tamper, a jacket made of uranium. The neutrons from the fusion stage strike this tamper, causing additional fission. Unlike traditional chain reactions that slowly multiply neutrons, this setup delivers a sudden burst of neutrons, enough to fission most of the uranium instantly. Since these are fast neutrons, even natural uranium, not enriched, can be used. This third stage greatly increases the bomb's overall explosive power. However, there is a serious drawback. Since the third stage is a fission reaction, it produces heavy radioactive fallout. That is why this design is used only when maximum destructive power is the main goal, with little regard for contamination. The United States' Castle Bravo test, with a yield of 15 megatons, is believed to have used a three-stage setup. The Soviet Union's Tsar Bomba, the largest nuclear explosion ever, had a yield of 50 megatons, half of its original 100 megaton design. The uranium tamper of the third stage was deliberately removed to reduce fallout. Modern nuclear weapon designs are even more advanced, often incorporating multiple stages. The initial fission trigger typically includes a fusion boost, and the third stage can contain a mix of both fission and fusion reactions. With such multi-stage configurations, we now possess the ability to scale nuclear weapons to almost unimaginable levels of destructive power. Whether we choose to do so, that remains a question not for science, but for the conscience of humanity. By now, you might have realized nuclear weapon is not the name of a single bomb. It refers to an entire category of weapons. And yes, there is more to come. Some are tailor-made for specific purposes. Others are designed to be extremely dirty. That brings us to the neutron bombs. Earlier, we saw that fusion reactions in hydrogen bombs produce a large number of free neutrons. In three-stage bombs, these neutrons are used to trigger an additional fission reaction. But what if the neutrons themselves were used as the main weapon? It may sound strange, but that is exactly what the neutron bomb was designed to do. Neutrons have a unique advantage. They are very hard to stop. While gamma rays can be blocked using dense materials like lead or thick concrete, neutrons behave differently. The reason lies in atomic structure. You might have heard that most of what we see as matter is actually empty space. This is because an atom consists of a dense nucleus at the center, surrounded by electrons orbiting around it. The space occupied by these electrons defines the overall size of the atom. But compared to that, the nucleus is incredibly tiny. If an atom were the size of a football stadium, the nucleus would be like a peanut at the center. That means most of the space we consider part of an atom is in fact empty. Still, this space is not easy to pass through. Electrons constantly occupy it and create a negative charge cloud. If another atom tries to enter, the charges repel each other. Even light, being electromagnetic, interacts with this charged space, which is why solid objects are opaque to it. But neutrons are neutral. The negative charge of the electron cloud does not affect them. In a solid object, atoms are packed so closely that even light cannot pass through. But to a neutron, the same solid appears as widely spaced nuclei floating in vast empty space. They are oblivious to the electron cloud. That is why neutrons can pass through thick materials like concrete or lead quite easily. This does not mean neutrons never interact. They can collide with nuclei along the way, but such interactions are rare, allowing them to travel much farther through matter than most other particles. This means neutrons can easily penetrate bunkers, fortified buildings, and armored vehicles like tanks, causing harm to the people inside. When a large number of neutrons pass through the human body, some collide with atomic nuclei in our tissues, leading to severe radiation damage. They can also make certain atoms temporarily radioactive, adding secondary radiation effects. So, the main damage from a neutron bomb is not from the explosion, it is from radiation. A neutron bomb is essentially a modified hydrogen bomb. Its explosive yield is minimized, while its neutron output is maximized. The goal is to kill living beings through radiation while causing minimal damage to buildings or equipment. Death may not be instantaneous. It can take hours or even days due to internal radiation damage. Because the fission stage in a neutron bomb is very small, radioactive fallout is limited. The secondary radiation from neutrons also decays quickly, within weeks. This allows the attacking army to occupy the affected area soon after the explosion, finding infrastructure intact but people dead. Neutron bombs were developed and stockpiled during the Cold War. However, Most of them have reportedly been dismantled today. Among all the weapons of mass destruction, the Cobalt bomb is considered the dirtiest. It belongs to a special class known as salted bombs. Earlier, we saw that radioactive fallout is one of the biggest drawbacks of nuclear weapons. But what if fallout itself were the objective? That is the idea behind salted bombs. In a typical three-stage bomb, uranium tampers absorb neutrons from the fusion stage and trigger a further fission reaction. But in salted bombs, the tamper is replaced with an element that absorbs neutrons and becomes highly radioactive. Elements like zinc-64, tantalum-181, and sodium-23 can be used for this purpose, but none are as devastating as cobalt. When naturally occurring cobalt-59 is used as the tamper, it captures neutrons during the explosion and transforms into cobalt-60, a deadly radioactive isotope. The explosion vaporizes the cobalt and spreads it as fine particles over a vast area, creating intense and long-lasting radioactive contamination. Not just a bomb, but a radioactive cloud with a half-life. The terrifying property of cobalt-60 is that even in very small quantities, it can cause severe radioactive damage. Just 1 gram of cobalt-60 is enough to make a square kilometer of land lethally radioactive. At that level, even 15 minutes of exposure is almost certainly fatal. To make matters worse, the radiation from cobalt-60 does not decay quickly. It takes at least 125 years for its intensity to drop to a safe level. This means the affected area will remain uninhabitable for well over a century. The total surface area of Earth is about 510 million square kilometers. Theoretically, spreading 1 gram of cobalt-60 per square kilometer would require only 510 tons of cobalt to contaminate the entire planet. A cobalt bomb could wipe out not only the entire human race, but also countless other animal species. Of course, a single bomb cannot distribute that much cobalt. But if multiple bombs were used strategically, it could be possible. That is why the cobalt bomb is often referred to as a doomsday weapon. This is not about winning a war. It is about sterilizing a planet or triggering mass extinction. Officially, no country today possesses such bombs. But the technology to build one exists, and many nations are capable of doing so if they choose to. In the wrong hands, this is not just a threat to a city or a country, it is a threat to Earth itself. A hafnium bomb is a type of nuclear bomb, but it does not rely on fission or fusion. Its energy comes from a different kind of nuclear reaction, something most people have never even heard of. As seen in earlier videos, excited atoms release energy when returning to their normal state. We usually refer to electrons doing this, releasing visible or ultraviolet light because the energy difference is small. But atomic nuclei can also be excited, and the energy involved is far greater. When an excited nucleus returns to normal, it releases powerful gamma rays. This process is what we call radioactivity. Normally, this release happens randomly. Even in 1 kilogram of radioactive material, we cannot control when each nucleus will emit radiation. But if all excited nuclei could be triggered to release energy simultaneously, the combined effect would be a huge energy burst, an explosion. That is the idea behind a hafnium bomb. From our laser video, you may recall stimulated emission, where an excited electron is triggered to release energy by a photon of the same frequency. The same principle applies to excited nuclei, which can be triggered by matching gamma rays. Hafnium is a stable element, but it has a rare metastable form called hafnium-178m2, where each nucleus stores about 2.4 mega-electron-volts of energy. If all these nuclei are triggered at once, the result would be a powerful blast. But here is the problem. Hafnium-178m2 is hard to produce and requires costly particle accelerators. And although small-scale stimulated emission has been observed, we lack the technology to scale it up. For now, the hafnium bomb remains a concept. No one has built one yet. A nuclear EMP is a type of nuclear weapon, but unlike traditional bombs, the damage here is not from the blast or radioactive fallout. Instead, the weapon is designed to create an extremely powerful electromagnetic pulse, or EMP, using a nuclear reaction. The idea is to detonate a nuclear device in the upper atmosphere. At that altitude, the air is thin, allowing gamma rays from the explosion to travel long distances. As they pass through the atmosphere, these gamma rays interact with air atoms, knocking out electrons. These free electrons then interact with Earth's magnetic field, generating tiny electromagnetic pulses. Here comes the key part. Both gamma rays and the resulting pulses travel at the speed of light. So, as the gamma rays continue to eject more and more electrons along their path, each new burst generates a tiny electromagnetic pulse that overlaps with the ones before it. These overlapping pulses stack together into a single intense and concentrated EMP. When this EMP reaches Earth's surface, it can cripple all electrical and electronic systems over a vast area. Since the detonation occurs high above in the atmosphere, no shockwave reaches the ground, and people are not directly harmed. But the electromagnetic pulse can destroy power stations, substations, transformers, distribution lines, street lights, and even traffic systems. It can disable computers, mobile networks, banking systems, and ATMs. Most transport systems will also be affected, as trains, airplanes, and even cars rely heavily on electronics. An EMP may not seem terrifying as there is no visible explosion or destruction on the ground, but in today's technology-dependent world, it can cripple an entire nation. A nuclear EMP can push a country back to the Stone Age, and because it is detonated at high altitude, its reach is enormous. A strategically placed, powerful nuclear EMP could black out the entire continental United States and parts of Canada in a single, silent strike. This is not science fiction. EMP weapons have been tested in the past. The most powerful EMPs come from high-altitude nuclear detonations, where gamma rays eject large numbers of electrons across a wide area. For nuclear explosions happening at ground level, the EMP is much weaker and limited in range. That is why such explosions are carried out in the upper atmosphere when the goal is large-scale disruption. However, there is a problem with this. A high-altitude EMP can also damage satellites in low Earth orbit, regardless of nationality. During past tests, some satellites were indeed affected, but at the time, only a few satellites existed. If such a weapon is used today, satellites from nearly every nation would be impacted. This is why the international community has banned nuclear weapons in space. Let us hope that line is never crossed again. In any nuclear reaction, the energy released follows Einstein's equation E equals mc squared. This means a small amount of mass is converted into energy in all such reactions. For example, in the Hiroshima bomb, about 64 kilograms of uranium was used, but only around 1 kilogram actually underwent fission. And even in that 1 kilogram, only 0.7 grams of mass was converted into energy. This is because in a fission reaction, a uranium nucleus splits into two smaller nuclei, like barium and krypton, and these products still retain most of the original uranium's mass. Overall, only about 0.09% of the mass turns into energy. Similarly, in hydrogen fusion, only about 0.7% of the hydrogen's mass becomes energy. The rest is retained in the helium fusion product. So, in both fission and fusion, less than 1% of the nuclear fuel's mass is converted into energy. But imagine a reaction where nothing is wasted, where 100% of the mass becomes pure energy. Such a reaction does exist, and it is the matter-antimatter annihilation reaction. When a particle meets its exact antimatter counterpart, they annihilate completely, converting all of their mass into energy. No fragments, no waste, only pure energy. This is the most efficient reaction allowed by laws of physics. A reaction with 100% efficiency. This means that to cause an explosion as powerful as the Hiroshima bomb, you would need less than 1 gram of antimatter. And with 1 kilogram of antimatter, you could match the energy of the Tsar bomber. the most powerful nuclear bomb ever tested. In theory, antimatter bombs could unleash destruction far beyond anything we can currently imagine. A weapon with no upper limit. But here is the problem. Antimatter is incredibly rare and difficult to produce. It is the most expensive substance on Earth. Creating even 1 gram would cost billions of dollars. So far, humanity has produced only tiny amounts, nowhere near enough to boil a cup of tea. And even if we manage to make more, storing antimatter safely, without it touching normal matter, is a huge technological challenge. So, thankfully, an antimatter bomb is still far from reality. And by the time we have the ability to make one, let us hope we will no longer have the desire to build such weapons at all. I hope this video gave you a clear and engaging overview of weapons of mass destruction. If you found it interesting, please hit the like button and consider leaving a comment. Your support really helps the channel grow. Feel free to share it with your friends as well. For more videos like this, do subscribe to the channel and turn on the bell icon so you never miss an update. Thank you for watching.